Hello everyone. Today we are going to continue the study of groups, and in this today's lecture I'm going to give you some more examples of groups, and then we are going to start subgroups. So we are going to see some examples of subgroups and some tests for checking whether some subset is a subgroup or not. So let us begin. So let us see some examples of groups from first. First example is this. So we have to prove that the set of all nth roots of unity forms an abelian group with respect to multiplication. Abelian group, you already know what is an abelian group. Means where commutativity holds for every element. So AB is equal to B for all AB belongs to the group. So then that the group is called abelian group. So we have to show that the set of all nth roots of unity, that set forms an abelian group, and the composition is multiplication. So nth roots of unity means the 1 upon n power of 1, this is, and 1 can be written as 1 plus 0 iota to the power 1 upon n, and this you can write as cos 0 plus iota sine 0 to the power 1 upon n. Then this can be written as cos 2k pi plus, so cos 0 can be written as cos 2k pi plus 0 according to the period, and this sine 0 can be written as sine 2k pi plus 0, and this has whole power 1 upon n, so this 1 upon will come here, so cos 2k pi plus 0 upon n plus iota sine 2k pi plus 0 upon n, and this is by De Moivre's theorem. So here the value of k is from 0 to n minus 1. So this whole thing is equal to e to the power 2k pi I upon n, where k is this. So this is because of this rule. Therefore, the set of all nth roots of unity, the set is given by this 1 alpha, alpha square, alpha to the power n minus 1, where your alpha is 2 e to the power 2 pi I upon n, and value of k is from 0 to n minus 1. So this set is the collection of all the nth roots of unity. Now we have to show that this forms a group. Now this set is an abelian group with respect to multiplication of complex numbers. So we have to find the identity element, inverse of every element, so all the properties of a group. So first of all, the identity element 1 is there, and then inverse of any element. So all element from this set, they are of the form alpha to the power r, where r lies from 1 to n minus 1. So inverse of any element alpha to the power r is alpha to the power n minus r belongs to G, and we can check that this is inverse because alpha to the power r multiplied by alpha to the power n minus r is giving you alpha to the power n, which is your 1, the identity element. So identity element is there, and inverse of every element is also there, and when you compose two elements, then the result is also in the set. The closure property holds, and associativity is also there. So, and commutativity is obviously there. Alpha into alpha square will be same as alpha square into alpha. So this forms a group under multiplication, and in fact an abelian group. So let us see this example now. Here, this is the set G with all 2 by 2 matrices of this form A0, 0, 0, where A is a non-zero real number. We have to show that this set forms an abelian group under matrix multiplication. So again, we have to check all the steps, how we prove that the set is a group or not. Closure property, then associativity, identity element, and inverse of every element should be there. So first, let's check closure property. So we have to take any two elements from G. So let us suppose that A is this element A0, 0, 0, and B is this element B0, 0, 0, where A and B, they are non-zero real numbers. So these two are elements from G. Then let us check this A into B. So A into B by matrix multiplication, this will be AB 0, 0, 0. So if A and B are real numbers, non-zero real numbers, then A into B will also be a non-zero real number. So this product A into B will belongs to G. So closure property holds. Now let us see commutativity, because we have to show that it is an abelian group. So we can check commutativity here. So A into B is this AB 0, 0, 0. And AB can be written as BA because A and B are real numbers and commutativity holds in real numbers. So this can be written as this. And what is that? This will be B into A. So commutativity is easily proven. Now matrix multiplication is associative, that you can easily check. Identity element is also there. So identity element will be this 1 0 0 0, and this is an identity element in G. And because you can easily check that you multiply any element with this element, you will get the same element. So A000 multiplied with the identity element is giving you again this same element. So all the properties of a group are being checked. So this last one is left, inverse. So we have to take any element from G, and then we have to show that inverse of that element exists in the group G, in the set G. So A is this element A000, where A is a non-zero real number. Then inverse of A will be this 1 upon A 0 0 0. A is non-zero, so we can easily take 1 upon A. So 1 upon A will be a real number, so this element will be in G. Now, why this is an inverse of A? You can easily check. We multiply A and A inverse, these two elements, and you get the identity element. So now we have proved all the properties as commutativity, associativity, then identity, inverse, and closure. So all these things are there. So now we start a subgroup. So what is a subgroup? Suppose you have a group G with respect to this operation, multiplication. Suppose this is multiplication, G dot is a group. Then a non-empty subset H of G is called a subgroup of G if H dot is a group. Means the subset you are taking from the group, that should be a group in itself and under the composition of G. Because you can see that this composition and this composition, they are same. So when you are taking a subset and it becomes a group under the composition of G or under the induced composition, then it becomes a subgroup of that group. So you can also write it like this: a non-empty subset of a group G is called a subgroup of G if it is itself a group under the induced composition. This is the notation. H is a subgroup of G is denoted like this, with this, or somewhere. Sometimes you can also see like this notation in some books. Now, if you have a group G, then every group has two trivial subgroups, the group G itself and the singleton identity. This is also the subgroup. So these two are always subgroups of a group, and they are called trivial subgroups, and all the groups other than these two, they are non-trivial subgroups. Let us see some examples now. Now, we already know that this set of integers under addition is a group. And this Zn, this we have already seen that Zn is also a group. Zn means the elements from 0 to n minus 1. So this is a group under addition modulo n. You already know what is, how do we define addition modulo n? You take two elements, you add them, and then you divide by n. Then the remainder will be your answer. So addition modulo n is this. So, now, this set Z has integers and Zn also has the integers. So, Zn is a subset of Z. But Zn is not a subgroup of Z. Why it is not a subgroup? Because the operation is different in both of these groups. So, here as this becomes a group under the addition composition, but here we are saying that the composition is addition modulo n, so they are not same composition. So Zn is a subset of Z, but it is not a subgroup of Z. So we have written this: Zn is not a subgroup of Z with this notation. So the operation should be same. So Zn is not a subgroup of Z, as Zn does not have the same binary operation as that of Z. So this you have to check that the operation should be same. Now this group 1 minus 1 iota minus iota with these four elements, and this H this subset with two elements 1 and minus 1, this becomes a subgroup of G. So this is a subgroup of G. The operations are same in this. Next is this the set of all even integers under addition. This becomes a subgroup of this all the integers under addition. So operation is same. E is a subset of I, so this becomes a subgroup. All the properties you can check in these both of these examples. This in this H, this subgroup, you can check all the properties of groups, they are being satisfied, and here also you can easily check. Now next we are going to see the subgroup test. So how to check whether or not a subset H of a group G is a subgroup of G or not. So for that we have a number of tests. So here first of all we are going to see one-step subgroup test. So let us see this statement. Let G be a group and H be a non-empty subset of G. Then H is a subgroup of G if and only if A into B inverse belongs to H for every AB belongs to G. So you have a subset, a non-empty subset of a group G, and if you want to prove that it is a subgroup, then you just check this thing. A into B inverse, if it is a member of H, then your subset becomes the subgroup. So we have to prove this. Now, first we suppose that H is a subgroup of G, then we are going to prove that AB inverse belongs to H, and then conversely we suppose that this condition holds, and we will show that H is a subgroup of G. So first the condition is necessary. Suppose that H is a subgroup of G, and we have to show that A into B inverse belongs to H. So suppose that A and B are any two elements of H. Now, because H is itself a group, because it is given that H is a non-empty subset of G, and you have supposed that H is a subgroup of G. So subgroup means it is a group in itself. So because H is a group in itself, therefore if B belongs to H, then its inverse also belongs to H. So B inverse belongs to H. And by closure property, if two elements are there in a group, then their product is also there. So if A belongs to H and B inverse belongs to H, this implies that A into B inverse also belongs to H. So this thing is proved. We supposed that H is a subgroup of G, and then we have shown that A into B inverse belongs to H. Now let us see the converse part. The condition is sufficient. So suppose that A into B inverse belongs to H. For every AB belongs to H, now we have to show that H is a subgroup of G. So if we want to show that H is a subgroup of G, then you have to prove everything, the closure, associative, identity, inverse, all the properties of a group. So we are going to use the given condition. What is the given condition? Given condition is this: A into B inverse belongs to H. We are going to show all the properties using this thing only. So A into B inverse belongs to H. This is given to you. Now, if I take B is equal to A in that thing, in that one is this only. Just see this. So this is your equation 1. A B inverse belongs to H. This is the statement 1. So if I take B is equal to A in that, then that will be A into A inverse belongs to H. And what is A into A inverse? A into A inverse is identity. So identity belongs to H. That means identity element is there. Now I will show that inverse of every element is present in H. Now using the same condition 1. Now if I take A is equal to identity, because we have already shown that identity belongs to H, so I can take A is equal to E. So if I take A is equal to identity element, then identity into B inverse belongs to H by 1. Now what is identity into B inverse? That will be B inverse only, because identity, this will not change this B inverse, so you will have B inverse belongs to H. So what did you prove? You proved that B inverse belongs to H for every B belongs to H. That means every element of H has its inverse in H. So this condition is also proved. Now let A belongs to H and B belongs to H, so that A belongs to H and B inverse belongs to H. Then by 1, if B inverse belongs to it, that means B inverse is an element of H. That means inverse of B inverse also belongs to H. So by 1, A into inverse of B inverse belongs to H by the statement 1. We have this. So what is inverse of B inverse? That will be your B. So A into B belongs to H for every AB belongs to H. So this is giving you the closure property. So closure you have proved, identity you have proved, and existence of inverse of every element you have proved. Now associativity is obviously there. Why? Because H is a subset of G. So all the elements of H are coming from G, and associativity holds in G. So associativity automatically holds in H also. So H dot, this is a group, and if it is a group, that means it is a subgroup of G. So because what was the definition of subgroup? That subgroup means a subset which is in itself becomes a group, then it is a subgroup under the same composition. So this composition is same as that of G. So H becomes a subgroup of G. So we have seen both the sides, condition necessary as well as sufficient. First, we supposed this H, suppose H is a subgroup of G, then AB inverse belongs to H for every AB in H, and then in converse part you have seen that if AB inverse belongs to H, then H becomes a subgroup of G. Then using this condition you have seen that we have proved all the properties of a subgroup. That means the identity, inverse, then associativity, closure, everything we have seen. So this was the test which you can use to prove whether a subset is a subgroup or not. Now let us see this remark. If G is a group under addition, then the one-step subgroup test will be as follows. So if you are going to apply one-step subgroup test, then what you have to do? To see this, H becomes a subgroup of G if and only if A minus B belongs to H for all AB belongs to H. So, this is the same thing which is given in the test, but it is in the form of addition. In the theorem which we have seen, here we were talking about the operation multiplication. The binary operation was multiplication. G is a group. Here G is a group under multiplication. It is not written that it is multiplication, but we are using here multiplication because we are combining these two elements by multiplication. A into B inverse belongs to H for every AB belongs to H. So G is a group under multiplication. But when you have group under addition, then this inverse of a element will become minus B, because in addition you will be having additive inverse. This is under multiplication. You are having a multiplicative inverse, B inverse. So when you are combining two elements, you are combining by multiplication property. So A into B inverse belongs to H. But this statement, how will this statement change when the group is under addition? Then you will combine two elements by addition. A plus inverse additive inverse of B. And what is additive inverse of B? Additive inverse of B is minus B. So A plus minus B, that means A minus B belongs to H for every AB belongs to H. If this condition holds, then H becomes a subgroup of G. So that thing is written over here. Let us see that remark again. So if G is a group under addition, then the one-step subgroup test will be like this. H is a subgroup of G if and only if A minus B belongs to H for every AB belongs to H. So both the statements are same, they have same meaning, just they are looking different to you because the binary operation is different. In the theorem, we were using multiplication, but here we are using addition. So this is the change. Now we have another test. This is called two-step subgroup test. So here we are going to check in two steps. So it is called two-step subgroup test. Let us see the statement. What are the two steps? A non-empty subset H of a group G is a subgroup of G if and only if the following two conditions hold. So what are the two conditions? Number one, A belongs to H, B belongs to H implies A into B belongs to H. So you can easily observe that this is nothing but the closure property only. So first you have to check the closure property, and then second step we have A belongs to H implies A inverse belongs to H. That means every element should have its inverse in H. So closure and inverse, these two things, if you check, then that subset becomes the subgroup. So these are the two conditions. Now we are going to prove it. First we are going to suppose that H is a subgroup of G, and then we have to show these two things, and then in converse we suppose that these two conditions hold, then we will prove that H is a subgroup of G. So let us prove it. Now suppose that H is a subgroup of G. Now since H is a subgroup which is itself a group, because the subgroup is a group in itself, so closure property holds in H. If it is a group, then closure property holds there. So closure property holds in H, and therefore by condition, therefore because closure property holds, so condition 1 is automatically holds, because this is nothing but the closure property. So if H is a subgroup, then 1 is automatically there. Now, second condition will also hold, because you can see that every element has its inverse in a subgroup, because a subgroup is a group in itself. So it will have inverse of every element. So you have condition 1 and 2 both satisfied. Now, so this necessary condition one, there was nothing to prove. Now let us check the converse part. So in converse part, suppose that H is a subgroup of G which satisfies both the condition 1 and 2, that means the closure and inverse part. Both the conditions are given to you, and in H, which is a subgroup of G. Now you have to prove that it is a subgroup of G. Now, as H is a subset of G, therefore associativity holds in H also, because all the elements are coming from G, and G is a group, so it has associativity in it. So associativity hold in H also from there. Now let A belongs to H. Now we are going to see that every element has its inverse in H, and this is true. Why true? Because this is given to you here. A belongs to H implies A inverse belongs to H. So every element has its inverse in H. From second part, let A belongs to H, then by second A inverse belongs to H. So inverse is also there. Now you have to show that identity should belong to H. So A belongs to H. If A belongs to H, then A inverse, and A inverse also belongs to H. And by closure property, A into A inverse also belongs to H. And what is A into A inverse? That is your identity. So identity belongs to H. So you have seen that identity is there, and this associativity is there, inverse is there. Every condition you have proved, that means H becomes a subgroup of G. So this is called two-step subgroup test. So any test you can use, one-step subgroup test, two-step subgroup test. So basically in one-step subgroup test, these two steps are merged in one step. What you were proving there, you were proving A into B inverse belongs to H. If A into B inverse belongs to H, for every A B belongs to H, then H becomes a subgroup of G. So when you were saying that B inverse A into B inverse, so that means that condition is hidden there, that every element has its inverse. So, but in two-step subgroup test, there you are specifically saying that this condition is there. Now, finite subgroup test, this is another test to check whether a subset is a subgroup of not, subset is a subgroup or not. So this is finite subgroup test. Let us see that H be a non-empty finite subset of a group G. So here we are taking finite subset, non-empty finite subset of a group G. So in one-step subgroup test and two-step subgroup test, it was not given that the subset is finite or not. Here specifically it is given that you have a finite subset of a group G. Then H is a subgroup of G if H is closed under the operation of G. So only one thing you have to check, the closure property, because you can think that if you have a finite subset, then every element will have its inverse if the closure property is there. So that we are going to see in the proof, that you can easily check, because if you do not have that thing, then this cannot be a finite subset. So the statement is given in another form here. If H is a non-empty finite subset of a group G such that A into B belongs to it, that means nothing but the closure property only. A into B belongs to it for every A B belongs to it, then it is a subgroup of G. So this is the statement of the test. Now we are going to prove it, and we are going to prove it using the two-step subgroup test, because we have already seen two-step subgroup test, so we can use it here. Now, by virtue of two-step subgroup test, it is sufficient to show that A belongs to H implies A inverse belongs to H. So in two-step subgroup test, you have seen that a subset becomes a subgroup if it satisfies two conditions. Number one was closure, and number two was inverse of every element should exist in H. Now, closure property is already given to you, that A into B belongs to H for every A B belongs to H. That means only one thing you have to prove. If you prove that every element has its inverse, then you are done. So it is sufficient to show that A belongs to H implies A inverse belongs to H. Now, Let A belongs to H. Then A square is equal to A into A belongs to, by closure property. If A is there, then A into A should also belong to H. That means A square belongs to H. Now, if A square is there and A is also there, that means A into A square is also in H. Means A cube belongs to H. Similarly, A to the power 4 will belong to H, and so on. So that means the series will go on. A belongs to H, A square belongs to H, A cube belongs to H, A to the power 4 belongs to H, A to the power 5 belongs to H, and so on. But it will stop somewhere because it is given that H is finite. If it does not stop, that means it is going infinitely. The subset this subset H becomes infinite subset, but which is not true. It is given that H is finite. So this has to stop somewhere. Now, this everything was coming by the closure property. Now, so if this is there, thus the infinite collection of elements A square, A to the power 3, A to the power 4, A to the power 5, and so on must all belong to H. But since H is finite subset of G, therefore there should be repetition somewhere. That means there will be some stage where A to the power m will be equal to A to the power n, where m is greater than n. So we must have A to the power m is equal to A to the power n for some integer m and n, where m is greater than n and both are greater than 0. So then that implies A to the power m minus n is equal to identity. Suppose this is 1. Now, m is greater than n and greater than 0. That implies that m minus n is greater than equal to 1. So if m minus n is greater than 0, that means m minus n is greater than equal to 1. So this implies that m minus n minus 1 is greater than equal to 0. So if this is greater than equal to 0, then A to the power m minus n minus 1 belongs to H. Now consider multiplying this element with this, multiplying A by this element. If this is belonging to H and A is also in H, then by closure property, their multiplication, the product, this thing also belongs to H. So let us check what is the product. So A into A to the power m minus n minus 1 is giving you A to the power m minus n, which is identity by 1. So if these two, multiplying these two elements is giving you identity, that means they are inverse of each other. That means this A to the power m minus n minus 1 is inverse of A. Thus A inverse is this and this belongs to H. So every element has its inverse in H. So you are done. So H is a subgroup of G. So this is finite subgroup test. So you have seen 3 tests: one-step subgroup test, two-step subgroup test, and a finite subgroup test here. So now 3 possible ways by which you can prove that a subset of a group is a subgroup of not. So this we have seen in this test that how you are going to prove that a subset is a subgroup or not by using one-step test, two-step subgroup test, and a finite subgroup test. Now, if you want to prove that a particular subset is not a subgroup, then what you are going to show? So the subset is not a subgroup if any of the following condition holds. So let us see. Number 1, if you show that the identity element is not there in the set. So if identity element is not there, then it cannot be a subgroup. So if you are able to show this, then the subset is not a subgroup. Second, you find any one such element which does not have its inverse in the subset, then also this is not a subgroup. Exhibit an element of the set whose inverse is not in the set. So this can also be done. Now, number 3, exhibit 2 elements of the set whose product is not in the set. Means closure property does not hold. So if you prove any of these 3 conditions, then the subset will not be a subgroup. Now, so if you want to apply subgroup tests, so it doesn't mean that if it is a one-step subgroup test, then you have to check only that one step. So it is saying it is one-step subgroup test, but few steps are hidden in there that you have to just think about, and obviously you have to apply those steps also. So let us see. first identify the property P. This is what you have to identify. You have to observe what is the property P which distinguishes the elements of H. So if you are having some subset H, then there must be some property, some defining property of H. Means how you are going to identify that a particular element is in H or not. That means there should be some identifying property, that property P. So you have to identify what is that property. Number two, prove that identity element has property P. So first, once you have identified that property, next you prove that identity element has that property. So if identity element has that property, that means identity element belong to that set. That means the set becomes non-empty. So if you have non-empty set, that means now you can apply your test, whatever you are doing. Number three, assume that two elements A and B have property P. Next, you have to take any two elements that have property P and then prove that A into B inverse has property P. That means if you are using one-step subgroup test, then you prove that A into B inverse has property P. So first, you have to identify the property, the defining property of the subset, then prove that identity element has property. That means identity will belong to the set. Then you have to take any two elements and then prove that A into B inverse has that property. If A into B inverse has that property, that means A into B inverse belongs to H, which is your one-step subgroup test. So these are the 4 steps basically that you have to do. Now let us see some examples of subgroups there, and we have to apply some test. So let us see this. Number 1, this is given this group G where you are having all the non-zero real numbers under multiplication. So R star, this is the non-zero real numbers under multiplication. This is your G, and there is some subset H. All those elements of G such that X is equal to 1 or X is irrational. So what is the defining property here on the elements of H? That the element is either it is equal to 1 or it is irrational. All those elements of G are coming here which have this property. Now we have to prove that H is not a subgroup of G. Now it is to be proven that it is not a subgroup. So it is not a subgroup. How you can prove? So easily you can see that square root of 2 that belongs to H because it is irrational. But if it is a subgroup, then by closure property holds, that means under root 2 into under root 2 should also belong to H. But what is that? This is square root 2 into square root 2 is giving you 2, which is neither 1 nor irrational. That means it does not belong to H. So you have found an element here. You have found here element root 2, and root 2 into root 2 is not belong to H. The closure property does not hold. That means H is not a subgroup of G. Now there is another subset K, X belongs to G such that X is greater than or equal to 1. Then K is also not a subgroup of G. Why? Because 2 belongs to K. 2 is greater than 1, so 2 belongs to K. But 2 inverse does not belong to K. Because 1 upon 2, that will be less than 1. So that does not belong to K. So inverse of element is not there. Now let us see this example here. H is this subset ordered pair 1 comma B, B belongs to R. This is a subgroup of this group G, where you have ordered pairs A comma B. A is non-zero and B is this. B can be any. So A is non-zero and B, these both are real numbers. So and the composition is star given by combining two ordered pairs like this. AB star CD is AC comma BC plus C. So this is a definition of composition is given here like this. You have to use it. So you have to prove that this is a subgroup of G. So first H is non-empty. Why H is non-empty? So for first step we have to show that the subset is non-empty. It is non-empty because 1 comma 0 belongs to H. This is basically the identity element. So now there are two elements X and Y in H. So elements of this type 1 comma B and 1 comma C. Then X star Y, by definition this will be 1 comma B plus C, and this belongs to H. Why? Because B and C, if they are real numbers, then B plus C is also a real number. Therefore, X star Y belongs to H. for every x y belongs to it. So closure property is there. And now inverse. So basically we are using the two-step subgroup test here, closure property and then inverse. Now x inverse will be 1 comma minus b. This belongs to it. This is x inverse. You can verify. Why? Because x into x inverse is giving you the identity element 1 comma 0 by definition of star, which is given to you in the question. So by two-step subgroup test, this becomes a subgroup. And this is in fact an abelian group. Now, this is third example here. So again, matrix. You have 2 by 2 matrices of this form, AB 0, 1, where A is non-zero and AB, they are real numbers. We have to show that this is a subgroup of multiplicative group of 2 cross 2 non-singular matrices. You have a group of all 2 cross 2 non-singular matrices under multiplication, and this is a subset given to you. You have to prove that H is a subgroup of G. So let's see. Now, let S is equal to A, B, C, D, means the group which is here given to you, this uh, group of 2 cross 2 non-singular matrices over R, that is given by S here. So A, B, C, D, 2 cross 2 matrices, A, B, C, D are real numbers, and AD minus BC, non-singular means singular means the determinant is non-zero. So AD minus BC is non-zero. So this is your group, and we have to show that H is a subgroup of S. Now let these are two elements in H, A1, B1, 0, 1, and E2, B2, 0, 1. These are two matrices in H. So if they are in H, that means A1 is not equal to 0, A2 is not equal to 0, and B1, B2, they are real numbers. Basically, A1 and A2 are non-zero real numbers. And then we are using here one-step subgroup test. First, we are showing that Y inverse. What is Y inverse? So this element will be the Y inverse of Y, and this you can check, verify here that Y into Y inverse is giving you the identity. Now, X into Y inverse. So one step subgroup test was A into B inverse belongs to it for every AB in H. So first we have shown here that Y inverse belongs to it. Then we are showing that X into Y inverse belongs to it. So X into Y inverse by matrix multiplication, you can see that it will be equal to this. And so this is in H, that means H is a subgroup of S. Now you have another example here. G is a group, and Z is equal to Z belongs to G such that XZ is equal to ZX for every X belongs to G. We have to show that Z is a subgroup of G. So as we have seen the definition of center of a group, so you can see that this is nothing but center of a group. All those elements of G such that ZX is equal to XZ for every X belongs to G. So this is center. Basically in this example, you have to show that center of a group is its subgroup. So let us see, first of all, we are showing that it is non-empty. How we are going to show that it is non-empty? We are going to show that identity elements belong to the set. So identity element belong to the set. How we are going to show? We are going to show that identity element is satisfying this defining property of this subset Z. So what is the defining property? Defining property is this: all those elements Z such that XZ is equal to ZX. So identity, if identity is here, that means you have to show that X into E is equal to E into X. Now, so EX is equal to XE for every X belongs to G. So identity belongs to Z. That means Z is non-empty. Now let us A and B are two elements of Z. So if they are in Z, that means they are satisfying the property of Z. That means AX is equal to XA for every X belongs to G, and BX is equal to XB for every X belongs to G. Now, X into AB inverse. X into AB inverse will be this XA into B inverse. This I'm using associativity here, so XA can be combined together here. Now XA is equal to AX, it is given here, so XA will be equal to AX, so AX into B inverse Now again I'm using associativity, so this will be equal to A into XB inverse. Now again here XB inverse will be equal to B inverse X, because BX is equal to XB, and here you will get that B inverse X is equal to XB inverse. So this will be here, if you multiply by B inverse on the left hand side on both the sides, then this will give you the identity. So X will be equal to B inverse X into B, and so you will get B inverse X equal to XB inverse. So here XB inverse is written as B inverse X in the next step. So from here you come here. So this is equal to AB inverse into X, again by associativity. So what we have proved that X into AB inverse is equal to AB inverse into X. And what does that mean? That means by the definition of this subset, all the elements of G are here. All those Z belongs to G such that XZ is equal to ZX. So we have proved that AB inverse is satisfying this property. X into AB inverse is equal to AB inverse into X. That means AB inverse is present in that subset. So that means AB inverse belongs to Z. And from one step subgroup test, Z is a subgroup of G. So this is all about today's lecture, and what you have seen today, you have seen how to check whether a subset is a subgroup of a group or not. So we have seen three type of tests: one step subgroup test, two step subgroup test, and finite subgroup test. And we've seen some examples also how we are going to apply those tests. So I hope you like the video, and if you like it, you can subscribe my channel and you can share it also. So see you in next video with some more results on subgroups and groups. Thank you.